So today is officially October the 23rd, 2024. So today we're going to talk about clustering. I've got some math formulas up here. I might go do a little teaching here, but today we're going to talk about my other go-to tool, which is geospatial clustering, hotspots, cold spots, and GIS. And our GIS software has just made the an application of this. And Wilbert, if you want, make sure you, okay, mute yourself. All right. Our GIS tools have been really powerful so that you can click a little button, run the clustering tools, and you're going to start to see reds and blues. This is what everyone wants to see, because when we look at a map and you see something's red, what's it mean? Hotspot. What else? Danger, bad, or whatever we're looking at. Now, these hotspots might be different. With by mail voting, the hotspots might be something good. So there's some interpretation there when it comes to what you want to do, what you want to look at, and all those, what you want to do. And all those things are interpreted, as well as cold spots. Because when we look at cold spots of COVID, well, cold spots are actually good where there's low COVID rates surrounded by other low COVID rates. And I've got some math formulas right here that we're going to kind of look at later when I go through my research here. But one of the things what I've started to do is, and this is with Dr. McGinn. Philip and Mary met Dr. McGinn before. He's our resident political geographer. He does know a little bit of GIS. But what we did was we combined what you did last week with what we're doing this week. You know, I just kind of turn around, put them together. This is a brief, and I've talked about this before, but I really want to talk about the methodology because it really isn't all that hard to get all the data. In our TED Talk last week, or whatever it was the week before, I talk about all these big, gigantic sets of records. That's the hard part. Once you get the data, it's pretty easy. And there's a couple things that need to be curated, because when we start looking at rates, I have this X bar thing right here. It gets a little ugly from time to time. It gets a little bit ugly. But what we did was, at the zip code level, we basically went and mapped by mail voting rates. These are the percentage of people, this is for the 2020 general election, the percentage of people who mailed in their ballots in the mail. They didn't even show up for early voting. They never went to a polling center, whether it was during early voting, which is now, or on election day. And so we can see the patterns attached to this. 90 to 95% of the project, which is getting data like this, because when we look at voting records, we're basically looking at about 7 million records of everyone by zip code and by address of where they live, not what they voted for, but what they're registered as and how they voted. Imagine an Excel spreadsheet with like 7 million records in it. Excel doesn't do 7 million, by the way. Excel only does a million, a little more than a million, because of RAM and ROM and all that, computer garbage. So, but you can imagine turning all these 7 million records into something like this. This was the toughest part, and that's about the zip code. Because I mapped it at this level because the best scale at which we have COVID data is at the zip code scale. Okay? Because when we do GIS and we do geospatial analysis, the tough part is, well, what level of analysis are we going to collect data at? If the best scale for COVID is zip code, then even though I have voting precinct and block groups and individual addresses of all 7 million voters, they're going to go back to what? Zip code scale, because that's the best association that I have. So there's a lot of scaling issues that we have here. So we've got this map right here, but what we did was, this is hotspot analysis of clustering. So October 31st, 2020, this was what our map of COVID looked like. And all we did was, within each of these things, I have percent Republican, percent Democrat, percentage of people who mailed in their vote, income, age, all this other stuff. And what I did was, and this is, we're going to make these maps today, is I just looked at all the reds versus all the blues. Now, this is COVID. So COVID, like the map up here. I made a COVID map up here. And I know I talk about this a lot, but who made these kind of groupings right here? Me did. I did. So what's high? Everything dark is high, but you can see it goes from 13.6 all the way to 32.81. It's a pretty big division. And we can group these data different ways depending upon the story we want to tell. And that story, and hopefully when we started looking at the exercise, people were telling some different stories, because when we did the cancer rates, did anyone do the cancer rates and find them statistically different? 2 people should be raising their hands because we did that. Okay. So when we did that, because you grabbed the 10 counties and the 11 counties, I said, oh, go grab another 5 counties. And Philip and Mary happened to grab really low counties on one side, really high counties on another side, and said, whoa, they're statistically different now. And those are some of the things I was getting to kind of indirectly when we look at how to lie with statistics, how to lie with maps, how to lie when we talk about adjacency. Because when we talk about hot spots and cold spots, we use the word around. Okay? It's a high value surrounded by other high values. Around, surrounded by. What does surrounded by mean? Near, adjacent, next to, within a certain distance of. So we'll talk about all the different ways that we can express, spatially express around. Okay, because this little zip code right here, or this zip code right here, literally has one neighbor. So it's only quote unquote around one neighbor, whereas something like this is around 5 neighbors or 6 neighbors. So that's really unfair when we're doing calculations based on one adjacency pattern versus another set of adjacency patterns. So we'll get into some of the weeds with this. So even the hot spots and cold spots that we make are going to be dependent upon, first of all, the normalized values that we put in, and then the adjacency values. So we got metropolitan, micropolitan. We kind of looked at associations. And next week, we're going to start looking at what we call correlated statistics. So there are relationships between, if we were to graph these, and we talk about it a little bit today with clustering to kind of look at these here. Because in theory, if I were to look at a map and it was random, what would this map look like if everything was random? What color would the map be? Would it be anything? Would there be hotspots if there were random data? It'd be yellow. The whole thing would be yellow, right? Because we wouldn't have anything with significance in one direction, nor significance with anything in another direction. But I think that's really important. When I start to see the reds and the blues pop up, that means we're not looking at a stochastic or a random phenomenon. Okay. I know Cameron did that with the motor vehicle crashes, right? Did you do the hot spots and cold spots? Okay. But all you need to do is run some hot spots and cold spots, and I bet you you're going to see where there's hot spots and cold spots of data that's already normalized. And so we can do that. Maybe that's your position paper. Clustering patterns of motor vehicle crashes in North Carolina. So use these, apply these to already normalized data. So we'll talk about some of the caveats that are attached to this as well. I had another thought that I was thinking about too. Also, in the top of this thing here, we have a working hypothesis. So we had a working thesis that COVID rates will be higher. In some cases, and as part of this exercise, the previous exercise, you could have looked at something that just says, I want to see if income values are different. And so we have something called a one-tailed t-test versus a two-tailed t-test. So one-tailed means it's in one direction, where that one mean is one has to be the left or the right or the other, depending on if you're saying less than or more than, where that you would use a one-tailed t-test in this case versus, hey, incomes in cities are different than incomes in rural areas. Okay? And so it doesn't matter on what side of these they are, because in this case, what we did find was the exact opposite in this particular case. Another paper that we've got here This is a undergraduate student. She's one of our minors, and I'm actually taking her to something called the Transportation Research Board. Have you heard of that one, Josh? TRB, it's the biggest meeting of transportation professionals in the country. We got hooked up with this through the NCDOT, and we're part of something called the Minority Scholars Program, where it's basically transportation related stuff. Now we're GIS shop, so basically, well, GIS is pretty much, GIS, so our applications, but there's lots of interesting applications with like psychology, with materials, with vegetation, engineering. So as you can imagine, kind of in the state, NC State and UNC Charlotte kind of holds they do a lot of things with transportation. But this is an undergraduate student named Lamana. And what we were looking at here, and I'm pretty sure I did this methodology, I'm pretty sure was this. Reinforce anecdotal. I wanted to look to see if I do have some cluster maps. I really do. This stuff rings a bell, right? But what we looked at here was we made some maps of motor vehicle thefts in the NCCU campus. So these are motor vehicle thefts in and around the NCCU campus. And she had a theory or hypothesis, and she was just based on anecdotal evidence. What's the word anecdotal mean? Not based on fact, just, hey, I know so-and-so who had this happen or whatever. But based on her anecdotal evidence, she said that motor vehicle thefts around the NCCU campus were higher than the rest of the city of Durham. And so I extracted out just the data for the city of Durham because the collection methods are different for the areas outside of Durham as well. And so motor vehicle theft, the motor vehicle theft that occurs out here in Research Triangle or up in Bahama or wherever else is different than the ones that occur in the city just based on their GIS system. So you can think of all the logistics, the incredible logistics involved with something like this. And so NCCU campus is kind of right here. What's the word around mean? Around the NCCU campus. What's your definition of around? Not far from. How do I express that quantitatively? Within a distance. What's a good distance for you for around, Michael? 5 miles. Okay. 5 miles. So anything within 5 miles. And I think in this case, we did 1.5 miles or something like that. But 5 miles. So we picked out everything within our study. Oh, we did it within 1 mile. Okay. So she did it within 1 mile. And so we found all of the block groups within 1 mile because at the end of the day, what we want a sample. That's what we want. Okay, we want a sample. So we looked at the 12 block groups within 1 mile of NCCU campus versus the 88 within Durham City that were outside of 1 mile. And then the average motor vehicle theft rate was 45.15 for every 10,000 people versus 21.14 for every 10,000 people. Do you think this is going to be statistically different? Oh, it definitely is going to be. It's almost twice that. Almost twice that. And so you can see this 0.0044. What does this mean to you? When I see one tail just means it's greater than or less than. Okay, we're only looking at one tail on that normal distribution curve. Okay, I like to have it a little bit more flexible here. So 2 tail, so it satisfies this because this is half of this. And so I want it a little bit more flexible. And you can ask for a real statistician, which one they would use here, but I like this more flexibility with this here. What's this tell you? These are statistically different. Now, there's lots of different ways that we can word this. Okay, the null hypothesis can't be proven or is disproven, or we can't prove the null hypothesis. But once again, we do the same exact things here. But these are, it's clustering for 2023, clustering for 2021. And so if I think of it, I'll post this map up here as well. So I'm going to kind of talk about a couple things here. We'll do a little bit of math right here. talk about some examples, and we're going to get into the case study where we're going to map, kind of follow up on not the cancer map, but we're going to follow up on one of the other maps that we have. Now, some examples that we have here. Do cancer mortality rates cluster in certain areas with statistical significance? Now, like Mary said before, if it was just random, everything would be yellow. And that's what it would be. Where are COVID rates cluster highest in the states? Do patterns of data quality at the county level exhibit, and this is something I did a long time ago. Where are bear sightings the most frequent in Northwest New Jersey? So these are some of the maps that we looked at before. This is for the 2020 general election. These are the percentage of people who mailed in their ballot. Mailing it in, just literally, they never showed up at a polling place. Do you think there's clustering attached to this? Yeah. Here's our clusters. You know, so even people mailing in their ballot, which I think it's kind of interesting because this would be an individual choice from me to you. We can map that and highlight it with statistical significance. So we can say Wilmington, Charlotte, Asheville, Guilford, Forsyth County, and Research Triangle, they all mail in their ballots at much higher, statistically more rates than these other areas highlighted in blue as well as yellow. Now this yellow right here, we'll look at the formula right here. This could be really high, but it's just not surrounded by other highs. It's not a hot spot. And so remember what the definition of a hot spot is. High value surrounded by high values. And we'll look at the formula that we're doing a little bit. Okay, you know, kind of the algorithms to do this, but the GIS is going to run this for us. Some of the things that I've done in the past where there were black bear issues. These are bears in Northwest New Jersey. I think I've talked about this project before. In December, they used to have yearly bear hunts. Like I said before, my brother had started this project and passed away and kind of found it amongst all of his stuff here. And so I was like, let me turn this into a paper because he was passionate about wildlife and mapping wildlife and all these interesting things because there was a bear fatality in Northwest New Jersey the first 120 something years. And so there were a group of people hiking and I guess the slowest one got caught or whatever, you know. So, but how do we group these? Because previously when the New Jersey Department of Fish and Wildlife, they grouped it by townships. Okay, and these are subdivisions of counties, townships, and towns, and whatever. Now, what's the problem with a map like this? Why do you think you have no bear sightings here, but multiple bear sightings here? Is this little area right here? This one. Why are they avoiding these right there? Why are they avoiding them? Those little towns. What's that? Higher population. So they're also really small. So the chance of having a bear sighting in one of them is much lower than in this large township right here. So I grew up in Northwest right here, right where these kind of areas meet. And so when I moved out in 1995, there were really no bear sightings. And then eventually my bears have been kind of moving throughout the state. It's kind of interesting, you know, instead of kind of, you know, staying in the same place. And then by the time my parents left, they'd see bear every once in a while here. And then Dr. McGinn, he lives like right over kind of Central Jersey right here. So you can see they've been spread out, but this map is biased because each of these are different size. So what are some of the things we can do? Is there something that we've done in this class that makes the squares, you can create squares so that they're all the same size? Look at that, fishnet, quadrant analysis. Because this is typically, when we zoom in on the map, and I got a map in the GIS data, category 1 and category 2. These are like threats to people and threats to property. These are what your townships and boroughs look like. We have these kind of donut shapes right here because we have boroughs, townships, we got everything. We got a lot of weird things. And so once again, I don't want to go back and revisit this, but part of this project was to create these nice little quadrants. Now, what does this formula give you? Let's forget about this one for now. What does this formula give us? L equals the square root of 2 times A over N. What is L? What does L mean? the length. Okay, and then we got a length times the length. We can calculate the area and create that fishnet. Now, why do we use this formula? What's so special about this formula? What is so special about that length that it pops out based on our area and our n? What's n stand for? Sample size, the number of points that we have within this. Well, what's so special about that L? Why is it special? Why don't I just say, hey, every square is going to be 1 mile. Every square is going to be 10 miles. Forget the formula. I could do that if I wanted to, but why? What's the significance of this? Understand the quadrants. Why? What's that? The size shape. Why is this size so important? Based on the space at the end, so that we have enough quadrants so we can do analysis, but we don't have too many, so there's so many zero values. So this creates a happy medium between making sure we've got enough bare sightings for every square, but we don't have too many zero values. Now, what's the importance? You can create this Poisson distribution, a little graph, and all that other kind of fun stuff there. Also, what's the advantage of using squares? Some of you all maybe taken raster data before. What's the importance of squares? They're all the same size, exactly. So do I need to calculate densities? No. If every square is 5,207 feet by 5,207 feet, then I don't need to calculate density. I don't have to worry about that Cantor density stuff that we've done before. And so when we look at the quadrant analysis, we can see this right here. We ran that Kolmogorov-Smirnov test, and we showed that there was a difference between the expected and what we saw. I don't think anyone's taken field mapping this in the spring, yes.
Actually, I did take that, but I have a question about that test.
Mm-hmm.
So is it measurement of the outliers?
No.
Well, so with this one, it's also for the
Sorry.
no. So
Yeah.
Yeah, but does it also take into account the outliers for the?
No, because in quadrant analysis, basically the null hypothesis is that bare sightings display a random distribution, and this is a random distribution using our Poisson. So it's got outliers, we do have outliers, like this one here, we got outliers here or whatever, but the Poisson distribution accounts for those outliers via that normal distribution. And one of the things I want to do for field mapping in the spring is I want to go and collect elevation data using a GPS, my watch, a phone GPS unit, as well as a real world GPS, GPS unit, or now it's called GNSS, Global Navigation Satellite System or whatever. That's just the new fancy name for GPS. The GPS unit, and create elevation profiles to see how different these elevation profiles are using something like this versus GPS versus my little watch thing here. Because when I go running, sometimes there's like a 50-foot elevation difference between where I start and where I end, even though I start and end in the same place. Because this thing isn't very good at elevation. It mainly cares about my X's and Y's so it can calculate time. But I was interested in these kind of elevation profiles because all this test is just a non-parametric test to find the difference between these. And when we have elevation, we have a X and a Y, a distance and an elevation. All you're doing is fitting one curve on the X that we bring in. I'm looking to see if anyone's interested. Cameron likes. Yeah. Now, some of the other things we did were we ran a little bit of curve fitting here because when we look at point and polygon analysis, we ran a spatial join. I did a density analysis, so we don't have yellows next to blues. We have yellows next to brown, next to dark brown. So we do a little bit of smoothing And guys, a lot of times in geography, I don't like blues next to yellows. Okay, and this might be a situation where someone sees the same bear, time after time after time again, and we're getting, 73 sightings, when in reality, it's probably like the same bear 73 times, or people who interpret this bears being bears, which are not group 1 or group 2 sightings, to be threats to people or property. And so some of the things were that I ran a density analysis of these sightings, so you can see where these were. And so this death occurred up in northern Passaic County right there. And then I ran my cluster analysis, and that's what we'll kind of talk about today. So now I can look at hot spots and cold spots, clusters of bear sightings. And then some of the things we can do is we can look at relationships to garbage dumps, distance to the nearest water body, percent forest, percent land cover, all these other things. Because a lot of times when we see these bear sightings or deer sightings, they're typically going to be in rural areas, but not unpopulated areas, because we don't have the human bear, human deer interaction. So these are the areas that we actually, have it in right here. And so we can look at these sightings here around lakes, around people, and this is kind of over right here. This is called the Delaware Water Gap right here. And so believe it or not, this is New Jersey. A lot of people are like, that's New Jersey. Where's all like the chemical plants and all that stuff? That's New Jersey. Has anyone ever driven through there? No, that's New Jersey. But this is what we call a water gap. So there's this mountain range called the Kittitick Mountains, or part of the Appalachians that run through basically the Delaware River, which serves as the border between New Jersey and Pennsylvania. Has basically cut this thing through over hundreds of millions of years. So it's kind of a really pretty hiking area. So that's kind of the area where I grew up and spent a lot of my summers here. But that's where we also have a lot of bear sightings that you need to be aware of. So today we're going to talk about polygonal analysis. There are point patterns that we can attach to this. So the things that we'll be talking about today can also be applied to points, but I kind of live in polygon space with states, counties, and crime rates, and all these other things. And so a lot of times when we agglomerate these data at the enumeration unit level, states, countries, zip codes, the crime data that you've seen before. Now we've got a couple of metrics here. I've got one here called Moran's Eye. I've got a couple of local ones called local Moran's Eye. We're going to focus specifically on Gaddis Ord hotspot analysis. What's global? What's local? I mentioned this before. So what's a global metric versus a local metric? Exactly. So we're going to talk about what this Moran's Eye does, and it's just going to return a single value. What would be another example? What would be an example of a global metric? What are some of the global metrics we've talked about? Just non-spatial metrics for a data set. Mean, it's for an entire data set. Z-score is a local. All right, so we got mean, median, mode, standard deviation. We got Z-score. We got a Z-score. So for each county, it's going to return a Z-score. And then we'll talk about the Gaddis Ord hotspot analysis. And I really like these because when I took my first geostatistics class back, 2008, 2009, this was kind of starting to become new metrics that they got into. Now, Moran's Eye is the degree of adherence to Tobler's first law of geography. Oh, I've got to run this thing here. All it means is it clustered, dispersed, or random? Does it have a checkerboard pattern? Or checkerboard pattern? So I kind of like these because we're using the Moran's Eye, and the more specifically the local Moran's Eye, we can look for spatial outliers, which are just as important as clusters. Where are there high values surrounded by low values? Where are high achieving schools surrounded by low achieving schools? That's something people might want to look at. And so do we have clustered patterns, random patterns versus dispersed patterns? So we can run this Moran's Eye index. I've got some math here, but it just basically runs on a continuum. Runs on a continuum from -1 to +1 because it's standardized by something in the denominator here. But we've got dispersed, we've got random, we've got clustered that run in these kind of different directions right here. Now, I'm going to show us a formula and I'm going to kind of go back to this. We've got this formula. You can see that I put it up here and I'm going to kind of point to everyone and hopefully everyone can see this right here. So I've got this formula right here because I've got the little sigma notation. What's that sigma notation mean? Add it all up. Just add up all that stuff with all the different weights right here. And so I've got the little formula right here, the crux of it. So I have x of I, which is one of the polygons in question, and we're just going to go around to all the surrounding ones and do x of I minus x bar. What's x bar stand for? Not absolute value, the bar on the top. Mean, exactly. So we got the mean. So the difference between the mean, we got the one next to it, the difference between the mean, and then they subtract the difference. Let's throw this into Excel. Okay, and let's kind of get all these values out of here. So when we start running this, okay, I have x bar right here is equal to 5, x of I, x of j, 6. I have a high I value. And all I did was just run a little Excel formula right here. So what are we looking at right here? I have one of the values which are close to the average, another one which is really, really high, and it returns a really high value. It's kind of okay right here. Okay, we've got these values here. If this value is close to the mean, are any of these really going to be hot spots? Probably not, because high surrounded by high. If you're not high, then guess what? Hot spot. Not hot spot. And so what it starts to take into account are things like this. I have the average is 5. I have a 10 next to a 15, and this is 2. A 10 next to a 20, this is 3. A 10 next to a 3, which is -4. So I kind of just pop these into a formula. So it starts to tease out these hotspot situations. 3, 0. And I'm going to show an example of some cold spots right here. I have a 1 and a 1, which is a 1. A 1, a 0, which is a 1.25. Because all this calculation is, what I did right here is just kind of throw these in. And all we do with hotspot analysis is, all right, if it's above the mean, we make it red. Below the mean, we make it green. Because you notice these high values are getting teased out, whether they're above the mean or below the mean, which basically means, unintended, which basically means they're in a cluster. They're high surrounded by high or low surrounded by low. It's above the mean, we'll make it red. If it's below the mean, we'll make it blue. So all this nasty, we got all this basically nasty math stuff that goes on to give us some I value, which converts it to a Z value and then a P score. Because we got maps like this right here. We look at a map like this right here. I don't know what we're mapping right here, but when we want to run local Moran's I, it says that it's random. I got a Z-score of -0.57, a p-value. So whatever phenomena we're looking at here is random. There's a good chance I can just throw values up like this, change my symbology editor, and it's going to appear something like this. Now that's not what I like. I like to see clusters and hot spots and cold spots and all that other good stuff with each other. And so local Moran's I identifies clusters with similar values of magnitude, regardless of highs and lows. There's not too much going on right now with local Moran's I, because these days, all they do, or what I like them to do, is tease out spatial outliers. Because I use clustering, I use the get org, give me the hot spots and the cold spots. Hey, let me go through and find some values that are high surrounded by high. So this is the local Moran's I. So this Moran's I, it's going to run a single value for the entire data set for median age. income or whatever phenomena that we're looking at, and it's just going to return a single value. So we could say things like income is very clustered while spending on fruits and vegetables is not. That's good as well. And then we can look at local Moran-Xi. More of our, these days, more of our local Moran-Xi get weights. This is the math that goes on behind this. You know, we can, just to be honest with you here, so that we can look at our raw data. And what I like to look at is when we look at local Moran-Xi, it'll say high, high. High values surrounded by high values. Okay, that's great. What I like to see are lows surrounded by highs, highs surrounded by lows. Because in theory, when we talk about Tobler's first law of geography, in theory, highs should be around highs, lows should be around lows, mediums should be around mediums. That's the way geography works. Now, once again, surrounded by. Oh, why are you talking to me? Okay. So there should be a reason for this, because to me, I like to figure out the whys on this when we've looked at cancer rates and all that other good stuff as well. So we look at things like literacy rates in China. Hey, we've got a high surrounded by high, high surrounded by high. That's self-explanatory. But here, this area right here, this is a low surrounded by high, meaning these should be high, but they're low based on the surrounding values. Right here is low surrounded by low, and then we don't have any high surrounded by. Because at the end of the day, with these provinces, we're making these maps ourselves. I need to make better examples. Now we can look at age-graded death rates. These are these death rates that we calculated before. Let's see what we've got here. We've got some low lows, high highs, clusters right here, and then nothing else. So we can look at these with statistical significance. We've got median household income. What do we have sitting right here? We've got a low surrounded by high. And a low surrounded by high. So we can look right here, this one right here. This is a low surrounded by high. Based on what? Ever medians. Now, should I make a good comment about outliers? All right. This is where outliers really wreak havoc. You have one of these values that are super, super high. What's that going to do to your average? Move it up or move it down. And so these calculations are going to be based on your average, which might be skewed based on one of those values. And so when we run these in Excel or we run these in our hotspot analysis, we run into some major problems. And then here's just some more. Because what it does is it creates this LI, this kind of local index, and the variance, and then we get some type of z-score that's converted to a p-value. Because at the end of the day, what do we care about? I like the z-scores, but I like the p-values. Okay, we got a p-value here, and you can see the associated z-score with these p-values. And that's what I care about. And even in this metric here, we can see some lows surrounded by lows, highs surrounded by highs. To me, this is powerful for looking for spatial outliers. And we had a student a few years ago where he did school analysis. Because we could do this with points. Hey, here's a map of all my schools. Let me look for all the hot spots of EOG scores, EOG success rates or whatever. So one of the things we can do is, let's look for the spatial outliers. Let's look for the highs surrounded by lows in neighborhoods where we would expect them to be low, but they're high. What are they doing there? Do they have some sort of after-school programs? Do they have ESL programs? Do they have enrichment? I don't know what they do. That's what one of our students did a few years ago. For the other schools right here, where they're low surrounded by high. Now, this isn't correlative statistics. So we can throw all these things into a big regression model based on income, race, other metrics, socioeconomic, demographic metrics that we can throw in to predict these. So these are just based solely on location, solely on location. Now, the other thing we have, and this is what everyone knows and loves, is hotspot analysis. You know, I love it too. These tools are relatively new. This is like the last 15 years or so. These things have come out to make these nice, pretty maps. Because we know what all this stuff means. It's just Z-scores here. And you know what? I can go into my table of contents and I can just say low hotspots, hotspot, not significant, hotspots, hotspot, hotspot. I can change all this. I can manipulate this as well. And so what we do here is we run these calculations again here, where we look at the difference between the value in question, because this is local, and its neighbor. So here, what neighbor means. You know, neighbor can mean a lot of different things here. We've got 7 different definitions of neighbor. Then it also looks at its relationship, high value relationship to the mean, to figure out if it's hotspot or a cold spot. So hotspots, high values surrounded by other high values. You can't forget that. Okay. Now, if you want to find high values surrounded by low values or spatial outliers, you go back to local Moran's eye, or go back to the local Moran's eye to look for the high, low, low highs. Those will be teased out. They will not be teased out here. So if we have a really high crime rate that happened to be right here, and it's surrounded by other low ones, it doesn't matter because it's not a hot spot. High surrounded by high. Cold spots, low values surrounded by other low values. And what we did here, did I talk about these maps? I think I've talked about these maps. These are crime maps in Winston-Salem between 2005 and 2007. You notice the shape of Winston-Salem's changed a little bit because it annexed a bunch of land. So we wanted to look at, I was working for Winston-Salem State University at the time. What we wanted to do was see how the tenor and dynamics of crime changed between 2006 and 2005 and 2007 had changed, because in 2005, I didn't have the crime data for the areas right here because it wasn't part of the city. It was part of the county, and the sheriff's office kept that in a separate place. So I couldn't do the appropriate calculations. And it wasn't until 2007, because I think the annexation happened in September or October of 2006. So even looking at 2006 was going to be a little bit jaded. So what happened when we look at the hotspots? Where'd the hotspots go? Actually moved from a kind of downtown to kind of a little bit south. They kind of gobbled up a bunch of crime over here. And we highlighted some of these differences previously when we looked at descriptive, spatial mean, spatial median, when we looked at the entire set of points right there. But we can see how hotspot analysis is used. I think anyone can understand what we're looking at. There's just a lot of data prep going on here because these were crime rates. If I were to do the total number of crimes, it's a bad idea. Why? Because, well, more crimes will happen, more people are. And so we've got to circle back not only to the age-graded cancer mortality rates and things like that. Mainly, I've been talking about the cancer mortality rates because doing the age-graded rates is a really kind of circuitous, difficult process to do age-graded rates. But we can see these have moved. You know, the hotspot has actually moved a few miles to the south. So the high is surrounded by the highs. This is kind of, I don't want to say a bad map, but I had to print this out in black and white at one point in time. So you can see how I changed the hatching each of these with hot spots and cold spots, because we were mapping data quality. You go to the North Carolina GIS website or the NCDOT website, you can download all the roads. And basically, are those roads correct? No. You know, they have the wrong speed limits in there. They're not even lined up in the right place. So we did some procedures to kind of go through and match these things up. And you can see where the best data were and where the worst data were. Some other things we can look at are prison reentry density mapping. So I work for something called the Center for Community Safety, where these are the number of prison reentrants per 1,000 people. You can see that it's definitely clustered. And so we can look at the clustering high values and low values with statistical significance. So perhaps the appropriate services can be provided in these particular locations. So essentially what we do is we create these big, gigantic scores right here. So you can see the I and the J's and the means. You can see at the top where we're subtracting the difference between the means. So I don't want to get into this stuff because basically at the end of the day, what do we want? You know, we got the X bar and I want a red or green. So we can look at things like COVID-19 incidence rates, March 28th, 2020. So right at the beginning of the pandemic, we can start to see where COVID rates were grouped at the county level. Here they are at the county level for the entire United States about a year later. Here are COVID-19 hot spots and cold spots in early 2021. So you notice that COVID kind of moved from here over to there. I think that's kind of interesting. And then what is this one here? This is June 12th, 2020. So this is before the general election. Eventually, around the time of the election, it kind of went all the way around Fort Bragg or Fort Liberty. Why would it go all the way around? Why wouldn't it go into Fort Bragg or Fort Liberty? What was that?
Troops coming home.
Troops coming home. Also, they were probably on lockdown, you know, so
Yeah.
so you're not really allowed, you know. So I assume there was probably a lot more practice taking place on and around the Army base related to that. So it kind of made a big kind of U, right, which I thought was kind of interesting and telling. And then you can see this manifested with hotspots, the hotspots, we're emerging hotspots, emerging cold spots. So I can start to compare these because what we're going to do when we run this, we're going to get something called a bin. And we're going to say -3, -2, -1, 0, 1, 2, 3. And -3, -2, -1. It's just going to convert those p-values to a color. And this tool is nice and neat. And we're going to kind of run some examples of these as well, because there's lots of different ways we can express these. We can look at, hey, you know, hotspots to hotspots. These dark areas right here around the time of the election, hey, what are things that are going from no clusters to hotspots? That's what we call an emerging hotspot. What are things that are going from no clusters to cold spots? Meaning, you know, low mail-in by votes. And you can see these areas in blue are all the areas where people between 2016 and 2020 were not mailing in their ballots. Then percent have changed. So there's a lot of, you know, the only limitations with these are your creativity. And so these last few maps, I really worked hard to, you know, compare the 2016 to the 2020 stuff, select by locations. Some of the things that you had to do for the last exercise. You're like, how do I run this spatial query before you can even go and prep your data for anything? This is a project that we did with a student named William. And he wanted to see if there was a difference between crime rates before COVID and during COVID. Now, what do you think? Probably a difference, right? This is proof. This is statistical significance because you can see, hey, look, total number of crimes went from 8,008 down to 6,647. Now, do these numbers here have any degree of statistical significance attached to them? No, they don't. How can I do this? Now, these are the number of crimes in the study area because I have to go and calculate these for block groups. And block groups entirely within Durham because I don't know what type of crime is happening outside of Durham. And then we have block groups and zip codes that transcend the boundary, and I can't prorate them or calculate or do whatever here. And so this is what the student did. So these are 100 block groups. When we look at census, block groups are subdivisions of census tracts, and census tracts are subdivisions of counties. So within states, counties, tracts, and block groups, we can count total number of people, you know, total, you know, age, race, gender, education, attainment, access to transportation, all those things that you calculate on the census, we can get at this scale. Because that's what we're gonna do next week when we talk about correlation. I know how many people are here, so I can just run a spatial join and calculate the crime rate. Now, the reason why I don't have this area mapped right here is probably because this block group goes right here. I don't know how many crimes occurred here, but I know how many crimes occurred here, so I can't really do the rate because it's only partial for this block group. Does everyone understand why I'm only working with everything within the city? This is what we nod and say, yeah, I think so. Okay, I can't, there's a block group right here. I can't work with this because I don't have the county data. I don't have the county data. So if I say, hey, 12 crimes occurred in this block group, but 12 crimes only occurred right here because I don't have the data for this. And this is what we call logical consistency. Okay, logical consistency. Because I have to go to another place to get the Durham Police Department data, Durham Sheriff's Office data, which has different standards, different way to collect these, different GIS system, different attributes. So they don't call it, reported crime. They just use a whole bunch of different things. And so what we did here was I just ran a hotspot analysis. These days, this is what they give us. So hotspots, cold spots. You can see between 2019 and 2020, the number of hotspots went from 20 to 21. The cold spots went from 5 to 6. Now, what does that tell us? Probably high crime is more concentrated than low crime. Okay, I can live with that. But I got to make sure I got to go back. Okay. But what we did find was that when I ran a two-tailed t-test and I just averaged up the crime rates for these 100, averaged up the crime rate for these 100, crime rate actually went down a little bit. Went down significantly, but it was just, there's so much variance right there that it was difficult to say with statistical significance. It was like 93% or 7, I think our p-value was like 0.07, 0.08. Now, the one thing about the crime rates was that the actual crime rates went up for violent crimes. The violent crimes went really high up during COVID, which I thought was interesting, really interesting. Okay, now the other things, okay, we talk about high values surrounded by other high values. What's the word surrounded by mean? And so when we look at some of these parameters, we can see there's 8 different definitions of around that we have. What's a neighbor? Spatial relationships. So we have something called inverse distance. What's inverse distance mean? Have I used that word before in this class? What does it mean? I'm trying to think of when I used it because I'm going to use it in the future. Inverse distance mean that areas close are going to have more of a weight than areas further away. So basically, first one's just like a weighted average. The second one's like a weighted average as well. This means that things that are twice as close are going to have 4 times more of a weight than things that are further away. I have a fixed distance band. What do you think that means? That's just a buffer. Anything within 10 miles is my neighbor. That's it. You're within 10 miles of me, you're my neighbor. And then I have something called contiguity. What's the word contiguity mean? Borders. So I have something called edges, and edges only corner. Meaning if we share a corner, are there any states in the United States where like 4 states come together at one point? What is it? Arizona, Utah, New Mexico, and Colorado. The 4 corners, so you can switch hands and 4, corners right there. And so in that case, Utah and New Mexico would be neighbors because it includes the corners, where that they wouldn't be neighbors if we include this stipulation. Get spatial weights from file. I don't do that. Get zone of indifference. So usually I just do whatever's default, but I think I might have it here. When I go to these drop downs here, I could say contiguity edges only. And so now, and this is kind of interesting here. This is the last couple things we talk about before we go for a break. Is that when I run hotspot analysis on my crime rates for fixed distance band, I get these hotspots and cold spots, where that I run contiguity edges only, I get a set of hotspots. Now, which one's right or wrong? I don't know. Yeah, I don't know either. I just I click OK and run it and go, But if you want to change your results, if you want to say, hey, there wasn't that much clustering, I might go with contiguity edges only, which probably has, 5, 10 more hotspots than the distance band. Now, the last big thing that they've got here is what we call cluster analysis. This is like the fundamentals of artificial intelligence, machine learning. This is, real new stuff. And we talk a little bit about these with nearest neighbor analysis, things that we call decent polygons, service areas, but cluster analysis is kind of numerical taxonomy analysis, because these days when we create graphs, and remember that Poisson distribution that you had, what you have? You had an X value versus a frequency. Didn't we do something before with like median age versus death rates, right? And so we had different graphs with each other, because in math class, what'd you do? You just went over 5 and up 6. And what are those numbers, the 5 and the 6? Those are little hash marks. But these days, each of our axes could be a income in dollars versus death rate in deaths per 1,000 people. These are some of the things that we can start to get into, where that, I got my R squares, and we'll talk about that next week, where that I can create clusters based on 2 or 3 dimensional space, where this is what AI/ML really starts to do. Okay, now the stuff with the Chat GPT, that's what we call generative AI/ML. That's literally been around like 2 years. We're pulling from libraries and stuff that's a little bit out of my, not a little bit, a lot bit out of my skill set. But I can talk a little bit to these, where that we have, hey, let me grab one variable on another variable. Let me start to put these into groups. Age versus income, death rates versus these, and I can put these into multiple groups. This is what we call centroid here. Let me create 5 groups or 6 groups or 7 groups, so I can start to have groups that look alike. And next, I can get another axis versus another axis versus another axis, because that's what we're going to be doing next week with regression analysis. Hey, let me look for all the factors related to each other. But this serves as the fundamentals of artificial intelligence and machine learning, where I say, hey, these red things are alike when it comes to test scores, high school diplomas, percent student spending, and student teacher ratio. So you can see these schools or these school districts are all alike compared to the yellow, compared to the green, compared to the blue. They're all alike when we start to group these, not in 2, but 2, 3, 4 dimensional space, and we just group these. Basically, these things are all just the closest to each other. And there's different ways that we can group these. So one's called density, where we look for the most amount of dots. Here, this is probably just, these are the areas that are closest to each other, because it figures out what time this is going to be, so we can look at the centroids of these. Have we heard the word centroid before? What's that mean? Literally center. It's the center. So let's find the center of the points. All of these points are closest to this one. Can we calculate distance? Of course we can. We calculate the distance in whatever these metrics are. Of course we can. Distance formula. Square root of x squared plus y squared, or the square root of delta x squared plus delta y squared. Fairly easy to do. Now we can do this spatially as well. So we'll come to a good stopping point here. We're going to open up case study number 4. And so it's going to look like this, and then we're going to open up the exercise. So let's take about a 10-minute break here. And this is what case study 4 looks like here. And so these are these zip codes that we're looking at here. We're looking at age-graded cancer mortality rates, median household income, percent minority, spending on fruits and vegetables. Maybe we can start to see some correlations with things like age-graded cancer. This isn't cancer, this is heart disease, mortality rates versus income versus percent minority versus versus spending on fruits and vegetables. So let's open up case study number 4. We'll look for some clustering, look for some clusters, and then we'll start looking at the homework. So we'll start here at about 6:17 or so, give everyone an extra minute or so. Give yourself a chance to open that up.
Yeah, well, yeah. Right. Yeah.
You have an idea for the position paper?
Oh,
Oh, that's right, okay. Yes, I keep forgetting.
it's okay, that's like. I know we had talked, that one day, so I'm like back and forth, I want to give myself the extra work.
No, I wouldn't give yourself the extra work. That's the rich, I think it's the rich database that you want to. Just take.
I mean, maybe we could do a couple of things.
Yeah, no, that would be, no, that would be, that's a good data set. You can give. Good job.
Yeah, I think that's sort of. That's good.
What are the things?
And North Carolina.
Are you the one that was doing the, well,
Zip
zip codes?
Yeah.
Separating all the zip codes?
Well, that was already separated out. All I did was pull the ICD code, your copy that, I just pulled it out of the data set. Did a couple of things. Yeah, it's did it for me too.
Oh, wow.
I don't need anything
So you got the code of the type of cancer? You look, yeah. Then you match that with the zip code?
Because I mean,
The zip code where it happened or where they lived?
the way it was reported, because
I mean, you
it
could,
would be, well, I mean, it would be just nice, so that's you could have someone. Like, I had people like birth states would be like short. It's just like, so like the information, I feel like a birth state, like their birthday.
that would be their, visitor, or whether they moved here.
It could be. Or
Yes.
you really had no idea. There's the information, like the address of where they live. So it's like, it's like, all paper.
Cool.
It's pretty.
That's
It's about. To the biostatistics database.
After you die, you need a certain amount of time for staff. Because I mean, after you die, it seems like, oh, they lived here and here.
Right, yeah, like the newest data set I could get was like 2021. It's different, really, so.
So now I'm trying to look up my aunt, because my mother didn't tell me that she passed away. I got the mention. My aunt passed away and I didn't know. I was trying to look up about her and it was like 6 months or more before I was. More than like that name. On that table. I can do my homework.
What's this for?
I'm on a computer. So you gotta put GIS on the computer. Hopefully. I want to figure out a way to end this document.
working hopefully by Sunday. And basically, it's going over like the why questions throughout different parameters. And what did you know? So basically, like, okay, like why would I need to speed that? Okay, what is this like? And then you can go further into describing the specific information by using poison distribution, by using another formula. So basically, with your work, I would love for people to just take a look at it and find, okay, it makes sense. I mean, also have it, because that can also help you with your projects. So, no, no.
I was making something similar, writing it out for my project, like, these are metrics that I want to do. And this one is this one is this, yeah. I was doing everything.
Yeah, it's, you know, because too, like, when write position papers, it's like, okay, well, we're going to talk about population based on whatever rankings are. Okay, well, what would you do? So how would you use it? Would you go to this formula next? What's that? And that way it'll just, it's like a branch. See how what branch connects, and then that way, you know, if pretty much everybody's like, oh, yeah, that does make sense, I think you can use it for your position paper, because you're like, I get this method for this reason. The site breaks down, you see. I can see where it's basically like how can I find it in my slow section. This descriptive, inferential, and correlative spatial measures, and then like the more for those the why questions. So that we can interactive. That way you like push a button, you know, like okay, it's why. Yeah, we just is.
Are you gonna put it on like online?
Yeah, yeah. I don't usually, I haven't checked the next class, but usually there's like a discussion board section.
Yeah.
So.
Collaboration. You started.
Oh, collaboration?
Have a collaboration. Web-based tools.
So she here, I kind of. So I have. Difference. Let's see. So all of them. You know, it's like it's very. Except for you, it's success. So that one, I said, schools and classes, really. So. So. Yeah, we could open up the case study. Maybe look a little different.
What?
54.
Let me see. Does everyone's case study for it look different?
This originally it had like the virgin comments. Where that's,
Oh. Okay.
you know,
Let me put those up, my fault. Okay. Shoot. All right. Cause mine, they're all kind of. Shoot. This one, you download the new? Let me try this one more time. If not, we're gonna run straight today. Try that. If they're broken, then. Let's see that source. Source. That's the. Where'd it go? Yeah, okay. We're gonna play with exercise 7. All right. All right. I messed something up. It looks like, and I don't want to go through and do it right now because I'm gonna hurry and mess it up even more. So what we'll do, forget about exercise number 7. I'll do a quick demo on it. How's that sound? Because I feel kind of silly. Yeah, I'll do that. How's that sound? And then we'll open up the actual exercise. Yeah, that's what I'll do. All right, so while we're talking here, let's open up exercise 7 with the median age and all that other good stuff. We'll look at that. And I will show an example of case study 4. When you open it up, it looks like I missourced the data. So the actual zip codes is sitting somewhere on my computer and it's mad at you all because someone messed up. I don't know who to blame yet, so give me a second. I'm thinking of Andy, but we'll kind of, we'll jury's out on that one. All right. All right, so a couple things about this is that this is, this is cluster. I'll show an example here. So if I right mouse click and open up, the thing about this is when you open up the actual, and I'll show you a couple of GIS tricks right here. When I go to view and catalog pane, and I go to databases, this is what case study 4 has. And you can see it's got hospitals, major cities, zip code, AGDR, this stuff right here. It doesn't have the zip codes, final death rates. It doesn't have the SA zip codes. So I'm just saying I messed something up here. So basically it's trying to reference this case study 4, and it's saying, hey, I can't find these things here because these things are sitting on my computer, when in reality, they should be sitting on your computer in that zip file. And what I probably did when I made the project is I just dragged a couple of these zip codes over that are still sitting in like case study 3, case study 2, and it doesn't know where to find them. Does everyone understand that, I think? So it's a short way of saying, long way of saying, just blame Andy for the mistake and we can move on. So. All kidding aside, I made a mistake. Sorry, I have trouble saying that. So, remember, anyone ever see Happy Days? Does anyone know what Happy Days is?
Yeah.
Oh, good, someone does. What was the word Fonzie couldn't say that anymore? Never had it to say. Wrong. Was it? Yeah, we're wrong. The bonds? Anyone ever hear of that? Yeah, someone knows. Someone knows. All right. All kidding aside. So what we're looking at here are zip code, death data at the zip code level. What I'm looking at is I've got the rate, I tweaked it into age graded mortality rates because basically when we're mapping death rates, what are we basically mapping? Where the old people are. We're just mapping median age. We saw some correlation statistics with that before. I've also got income, percent minority, spending on fruits and vegetables, some of the data that we looked at previously, number of people, percentage of people who live below the poverty line, and per capita income. What's per capita income mean? Per person as opposed to household income. And then we have family income, which are households where the people are all related, which is going to be slightly different. So, Andy, what are you doing? Are you helping her?
Yeah, she doesn't have it on her new computer.
Have what?
She has,
Oh, GIS. Oh, okay. All right. I didn't know if we're doing case, just forget about case study 4. We're going to start with the homework because I messed it up. But I just wanted to show some neat relationships here because we're going to go through and do these all ourselves. But down here, under spatial statistics, we have something called mapping clusters. Look at all the different mapping clusters we've got. We've got build balance zones. Those are some of the AIML that we get into. Similarity searches, spatial outlier detection. We also have hotspot analysis. I think this spatial outlier detection, and then this cluster and outlier analysis. This is that local Moran's eye where it not only looks for high, low, low, but low, high, low spatial outliers according to means and some of the other measures. And then multivariate clusters. Here I'm looking at hotspot analysis. So I double click on hotspot analysis. This is what my metric looks like. And we're going to be doing this for homework exercise number 7. After this, we got exercise number 8, and then we're done with exercises. So you can focus a little bit more on the physician paper. So we'll have a couple of in-class things and a couple of the readings that'll be part of what we're doing. But we're going to kind of make a couple of assumptions right here, run a couple of things and see what we have here. I've got 2 feature classes here. My input feature class is going to be my zip codes. And my field is going to be my age graded rates. I have something called fixed distance band. But remember, we talked about this before, where these are all the different ways that I can express spatial relationships. And if you ever get kind of lancy here, watch what you can do. Click on the little I button, and this tells you all the different ways that spatial relationships can be conceptualized and calculated within the confines of this tool. So this tells you with all these nasty calculations. This tells you what the X and J is. How many X and J's are we have? Then we can throw a little weight in front of it, so we can do a weighted average with some of these if it's closer or further away. In some cases with these contiguity edges only and contiguity edges corner, if it's next to you, it's a neighbor and it's weighted the same if it borders you for 99% of it versus 0.1% of it, doesn't matter. And then we can calculate Euclidean distance. So I'll keep the defaults right here. But when we look at age graded rates right here, this is what our cluster analysis gives us. And this is really easy, really simple to run. Look what we got here. Got a map right here. So these are our hot spots. And I'm going to just drag this on top of us here where this is the age graded, it's not cancer, but it's heart disease mortality rates. What do you see up there in blue? Low rates surrounded by other low rates, high rates surrounded by other high rates with statistical significance. And to me, these things are map ready, okay? Definitely map ready.
Will you explain where the hit blue?
Light blue, oh, good question. Who has a good question? The middle blue versus the dark blue, one's at 99% confidence, 95 and 90% confidence. So over the table of contents. So these darkest blues, they have really, really low p-values versus lower p-values, but not quite as low as those. And so anything that's going to be the lightest blue right there, it's the p-value return between 0.1 and 0.05, 0.05 and 0.01 and 0.01 and less. Now, when we start looking at these, if I were to right mouse click and look at the brand new feature class, this is what it gives me here. It gives me a Z-score. It gives me some random score here, but GI fixed value. Watch what we do here, right here. If I can sort these, I have a bin called -3. Okay, I've got p-values. What do p-values mean? The lower, the better, right? Or the lower, the more cluster. 3, 3, 3, 3, -3, -3, -3, 3. And then it tells me it's a hot spot or cold spot if it's above the mean, below the mean. So all we're doing is converting a Z-score to a p-value and then coloring it in whether it's negative, positive. Do we really care about this stuff here? No, not really. I like for little bins right there, so I can see the -3s are going to be what? My cold spot, where the 3s are going to be my hot spots. So this is a high value surrounded by other high values with like literally 99.9% statistical significance. And we know what these Z-scores mean, right? When we look at a normal distribution, this has got a Z-score of 3.2. So this is really on one side. What are the chances of having something here by random chance? Really, really small. That's what it means. Okay, so any interpretation of these. And I'm pretty sure this is the number of neighbors that it calculated it for. So we had 13 neighbors, 8, 7, 9, 7, 6, 4, 12. So we were just looking at fixed, I think fixed distance right there. And then this bin tells you, do we make it dark blue, medium blue? What do you think the zero values mean? If the bin says 0, what color do you think that is? White. Exactly. White, I mean, it's not statistical significance. Why? Because we're looking at 0.37, 0.42, 0.95, 0.9, whatever. Pretty straightforward with those. Now let's run another one of these with the geoprocessing. Hey, let's see if there's a spatial relationship between age-graded cancer mortality rates and say percent minority. Or how about we do income? Instead of percent. How about median household income? Let's close one. What do we see here? So this is it for income. You see relationship here? Let's see what we got. So this area, especially right here, higher income, lower death rates. Think that's coincidence? No. Now, what we're going to look at next week is correlation, where we graph one versus the other. Let's watch what we can do as well. We can, gotta think off the top of my, think right here, but right mouse click. Create chart. Scatter plot. Properties. We've done this already, where that income what do you see right here? What happens if income increases? What happens to the age-graded mortality rate? Decreases. Right? How do I know it decreases? Number right there, right? Remember y equals mx plus b back in the day? That's just y equals mx plus b. Now we have something here called an r squared. That's not very high, so most of the variation with these values is it's going to be a lot different. Well, we can look at some other things, median household income versus, well, this is kind of obvious, right? Is there a relationship between income and poverty? Yes, obviously. What about spending on fruits and vegetables? What happens when income increases? Spending on fruits and vegetables does what? Increase. You think that's a coincidence? This thing definitely tells me there's not a coincidence. R squared, and we'll talk about what that R squared equals 0.38 equals to. So I like these here. Now these, once again, kind of circling back, these tell me all of the wheres with this, okay? And so I can extract out and look at the number of hot spots and cold spots and all these other things where that, I bet you these age graded rates, the income, I bet you is a lot more clustered than the age graded rates. So there's probably more randomness or more random numbers thrown into this, because I see a lot more white here than I do here. Now, why would we have randomness with that? Because we age graded it and did all these kind of strange calculations, which are gonna kind of throw in some other things there. Okay, but definitely see some relationships right here. We got Robeson County right here. Okay. But definitely some relationships with these here. All right, so now I'm done wasting everyone's time with those. Let's look at exercise number 7, and we'll open it up. We can start it for a little bit. Okay, I still got like an hour and a half, so we gotta think of stuff to do. I'm not gonna be here for an hour and a half now. And get some pizza. Okay. All right. And once again, this exercise to me is a little bit kind of higher level thinking here, because we're going to run cluster analysis on median household incomes. And this time we're going to run it on some of the different input parameters, some of the different definitions of spatial relationships that we have here. So when I run it using fixed distance band versus contiguous edges only versus inverse distance, we're going to have different number of hot spots and cold spots. So you could say, hey, median household income or death rates really aren't that clustered if you use one definition versus another. So we'll look at these here. Now, what we're going to do is we're going to map right here. This is median age. Okay, median. So we can see where age is higher, age is lower. See these? So these dark areas, show where the average age of the people is highest. In this case, median age. What's the word median mean? No pun intended. Middle. If I lined up every single person, that would be the middle age here. Okay, so you can see here, over here, it's about 47. So if we were to line up every single person in the county, the middle-aged person would be 47 years old. Why do we like using words like median or measures such as median as opposed to averages and means?
Because it avoids those outliers.
It avoids those outliers, exactly. And that's one of the challenges that you run into with cluster analysis. I don't want to go down too many rabbit holes here, but when you deal with small number problems, this mean gets really wonky really quickly. So that PhD student Alana that we worked with, we had to get rid of some of the values because we ran the cluster analysis and like it was blank. The whole thing was blank. Oh no, what happened? But when we looked at it, we saw there was like a zip code that had 4 people. 1 person died. So literally the death rate was like 250 for every 1,000 people, while all the other death rates were like 2, 3, 4, 5. Would that do the average? Jacked it up. So you didn't really have any hot spots and cold spots because your mean was just so far in one direction of your normal distribution. So the relationship between your median and your normal distribution, your average was just so far over because of these few outliers that we ran into. And then on the other end, if you had a population of 2 and no one died, 0, 0, 0. So we got rid of some of these things so that the mean values were working. Now, when we start throwing out zip codes, what's that do to your spatial relationships? It's a little wonky. Like, what if you're surrounded, or what if you're next to 2 zip codes that we threw out and made null? Well, you got 2 less neighbors for you to run this cluster analysis with. How do we do this? I don't know. We'll let someone else figure that stuff out. Okay, and these are all really, really good questions for kind of future research, to be honest with you. All right, so what we're going to do here, and I'll let you answer the first couple questions, is we're going to run hotspots. To me, two-tailed t-test, ANOVA, hotspots, they're my go-to statistical tools. So we'll look at some of these other tools. I'll let you look at some of these other tools and get to those. Chima's been sick for the last couple of weeks. I checked in on him last week, and he's not, he's doing okay, but he's been sick. But he's got really good interest in some of the geospatial statistics, probably much better than me. And I think him working on his PhD he wants to get into that space right there because it's ripe for research. When you open up ArcGIS, 1.0 versus 3.3, where we're at now, there's whole new sets of geospatial tools. All right, so what we're going to do here, we're going to map median age. We're going to go to analysis. We're going to go to tools. Did you unzip it? Does everyone have this, or did I mess it up? So I'm just going to point it Daniel. Let's get Andy helping him. Okay, all right, Dan. We're going to blame Daniel on that. No, I'm kidding. Because when you open it, you do see 2 folders open at, if we're looking at Windows. Okay. All right, so we're going to go toolboxes. And we're going to go down to spatial statistics. And we got patterns, high-low clustering, general G, average nearest neighbor. We're going to look at mapping clusters. Look at all the new tools we have here for mapping clusters, like balance zone, cluster and outlier analysis. Maybe we'll click on something with this here in a little bit. Hotspot analysis, multivariate clustering. These are all things that are a little out of my skill set. This is me. I can pretend I know what I'm talking about with some of the other things. Okay, because it's all great, we can run these, but make sure you're able to run the interpretation. That's why I like looking at those p-values and those pretty little graphs that it gives you, because it explains those, I think, a lot better than us trying to do it, with blinders on. So I'm going to click on hotspot analysis. And what we're going to run, right, hotspot analysis. And the good thing about this is the more input parameters you have, the better things you can do. But what happens if you have more input parameters? The more you can screw up. Okay, so make sure we're really intentional about making sure we know what a map should look like. Okay, when we run this, I bet you there's going to be some hot spots and some cold spots, so it shouldn't appear all the way like, white. All right, so our input feature class is going to be NC counties. Yeah, our input field, these are all quantitative data. So I'm going to go down to, what is it, median age. And then our conceptualization of distance is going to be what? We're just going to leave it at fixed distance band and let the algorithm kind of run it for me. So, and I don't need to do environments because we're not working with raster data. I'm just going to run this thing. So this is just going to map median age based on hot spots, cold spots, everything else. So what do I got here? This tells you where the younger people are. This tells you where the older people are. Younger people, older people. Now, when I look at the cold spots, hot spots, I've got 4, 2, 4. Oh, wow. How do I do the 4? How do I do the 2? How did I do 2, 4, 2? How do I know which one is which? Let's look at this one right here. What's this word bin mean? What's literally the word bin? Something you just put it in. And all it did was it just said, I've got a Z. Why is this bin 3, but this bin 2, but this bin 1? You notice anything about these Z-scores or these p-values? What can you tell me about these 2 p-values that are different than these 4 that are different than these 2? Confidence level, exactly. These are really, really small. So these are your 99 percenters. Then you got 1, 2, 3, 4. These are your what? Between 0.01 and 0.05. So these are your 95 percenters. And then these are your between 0.05 and 0.10. These are your 90%. And then after this, forget about you. Because we can sort these on our p-values and then see these associations here. Now, what are my cold spots going to be? Just the negatives. So let me do sort, descending, and what do I have? I've got one of them at this level, one of them at 99%. I got 1, 2, 3, 4. At this level, what do I have here? 1, 2, 3, 4, 5, 6, 7. Can we make any statements about this? You look at a map like this, what does it tell you? What can you guess? Probably lower age people are more spatially clustered than higher age people, right? That's probably about it. And this quarter kind of running from Orange County, Chapel Hill, Durham, all the way down here to, what is it, Scotland County right here. And then we've got this, why is this part of a cluster? Low, surrounded by low, but this is Camp Lejeune out there. And so it's so low that it's really low. but it's not necessarily part of a low cluster because it may be surrounded by other high counties. Those are some things to keep in mind. Okay. So we've got these here. Now, we can run it again, and we can do contiguity edges. So the next thing we can do is, we can go back, run the tool again, run the same exact thing on median age. And I run, contiguity edges only and run it. And guess what? I'm going to get a entirely different set. Different map, huh? And the interesting thing about this, and the thing that I like about this is, and we can see how it works, so we can look at all this kind of math stuff. It runs the same exact formula, but it uses different I's and J's here. So now this is using one method, another. Like to me, to me, this is the topic for a thesis. This is the topic for a position paper. And what would be the hypothesis for the position paper? And we can use a little more general. We can show how spatial relationships change hotspot, cold spot clustering. I think one of my more recent papers shows how it is, and then we use the statistics to do that. I want to see how different they are, see how different these are. Create a nice little plot here. So now we can put, contiguity edges only, inverse distance. Look at this. Look at this. So what I want you to do is, and we'll do, I always change some of these things here. You can do either question 8 or question 9. Oh, cool. And then you have to go create a new hotspot normalized map of something that you want, that you've derived from scratch or another project. Like, hey, go create some clustering of spending patterns. Go create some clustering, and I'll explain this in a minute. Because I always kind of go through and update these exercises every semester. So what you're going to do is you're going to fill out the chart. The next thing I do, getting a little bit further down, is you could answer these questions here, run a hotspot. We get 3 separate attributes. What do we have here? Contiguity, p-value. This is the number of neighbors right here. Okay, so this number of neighbors for this one right here, it counted 7 neighbors. All right. 1, 2, 3. Was that 7? Oh, maybe it is. 5. 1, 2, 3, 4. I don't know. I guess so. We might have set a buffer with that. I'm not really sure. So, but these were the number of neighbors that we had for this. And then that bin. What does that bin mean? You can see that it's white, so that's not part of the bin. So we should see some associations. The other things that we have: high-low, low-high analysis. This is another tool that we have here. So this is cluster and outlier analysis. Cluster and outlier analysis. So we got counties. Our field's going to be median age. Once again, We could set up all these same parameters, so you can go down a lot of rabbit holes. We'll just keep this the same. I like this a little bit. Oops. So what do we have here? You can see the general hot spots and the cold spots are in the same place when we ran median age. So we ran median age, but what do we have here? This is a low surrounded by high. What's going on in this county right here? This is actually where my daughter lives. What's in this county here that would make it a low surrounded by a high? Yeah, it's Western Carolina. So what age of people live there? Young people surrounded by a bunch of old. Right? So these dark ones here, these blues and these reds are your spatial outliers. Hey, low cancer rates surrounded by high cancer rates. What's going on in this county that bring about these patterns? Because in theory, that county should be low, but we got a university there. And then we have another one here that's a high surrounded by a low. So I don't even know what county this is here. Oh, this is just high age surrounded by low. And then what do you have right next door? You got a low surrounded by a high, right? So you kind of see these checkerboards right here. And it's also dependent upon what? The mean of the values, the mean, their relationship to the mean, and then we kind of throw them into that formula right there. So for number 7, we talked about that a little bit. All right, cluster map of population change at the county level. Can you calculate pop change with new fields? Did we do change detection analysis back in the day? Yes. And I'll just write the formula up here, even though we shouldn't, most of us should know it, but you're going to calculate, we're not going to do it here, but we're going to calculate a new field. Percent change. How do we calculate percent change? New minus old divided by old. Okay, so we're just going to do new as old divided by old. Me, I like to multiply the whole thing times 100 because I don't like to get values like 0.023. I want 2.3%. And when we start to look at the fields here, what is our new going to be? I think it's going to be 2010. That field minus 2000, all divided by 2000 times 100. We need to express that into our editor, right? Put that into our editor right there, so we'll make that calculation. What is going to be a number? Can you get, first of all, can you get negative numbers? Yeah, what would mean a negative number? What would a negative number imply? Population went down, right? Population went down. So the population in 2010 is less than the population in 2000. Can you get a number like 162? Could, really hard, It went from like, 3,000 to 7,000 or something like that. It's a lot, but it still could. So think of the numbers. Now, over a 10-year period, from maybe what you learned in Dr. McGinn's class, what type of numbers should we be getting between top 2000 and top 2010? Who's taken Dr. McGinn's classes here? You haven't taken any, Cameron?
It's just like a geography, geography.
Oh, okay, all right. So that's upper level. We're probably looking at numbers maybe between -10 to 30 or 40%. Maybe big counties like Wake County have really increased. Chatham County. So before you even run this, get an idea as to what a high value is. And then what you'll do is, then you got to run the cluster analysis on it. So now you got to calculate a new field, then run the cluster analysis on this. I think we can do that because everyone did really well on the change detection stuff, 7 weeks ago. And so I would refer to a couple of things, calculating new fields. So I've got a video in there called Calculating New Fields, refer to that. Because I guess I said you only had to run number questions 8 or question 9. Okay. So you only need to do one of these. So calculate a new field, number 8 or number 9. Calculate a new field and then run cluster analysis on it. And then next, create your own hotspot map of normalized variable that you derived from scratch or another project. What are some things that you've worked with already? Raw cancer mortality rates, right? You derived that. Spending on fruits and vegetables at the zip code scale. Okay, so what I want is just a nice, pretty looking cluster map that you've created from stuff that I haven't done already. So that's the data development. That political stuff that the political voting I did with Dr. McGinn, like I said, 90% of that is, all right, me making the data, putting it into those columns right there. And then it's just really easy to calculate because you get real weird values. I got to typecast some things. Typecast it wants to treat the number as a number, but we're treating it as a text because we can have zip codes that start with 0. North Carolina isn't one of those states, but we do. So I got to add extra zeros and it just gets really ugly, really. All right, let me see what else I've got here because I don't think I have any readings or anything like that. So just because I'm getting ready, unless anyone has any questions, So I think we've got enough to work on here. So when we look at cluster analysis, we've got exercise due next week. Case study, forget about it. I kind of went through it a little bit. I've got the presentation, the video. Tomorrow I'll post everything. And then I did post the book here. I love this book. Yeah, I love the book because it's software agnostic. Means that it's not specific for any software package, so it's not Esri friendly, but it kind of explains some of these clustering and calculations, pretty well. I like these, the distances and confidence intervals, and you get a sword and and all these things right here, your z-scores from Moran's eye, and then we get down to, and this book was written like 2005 or so. So this is just getting into this GI score right here, so just getting into the GI score. So, some of the things with the bins and all that, it's not even, hasn't really even been invented yet, to be honest with you. Some of these. And then you can see how it used to diagram it, back in the day. So this is some really good. This last paragraph is going to be essential here with factors influencing the GI star. So I like those before. Any questions for me? Any questions? We're all set. We got some good work ahead of us here. This is exercise 7. We only go up to exercise 8. So we only got one more exercise after this, and then we're you got a couple more readings here and there, and then work on the paper. Obviously to me, the paper is kind of the foundation for, what you might want to do for your thesis, for your project within our department, or maybe if you're a PhD student, some of the statistical methods that you're going to apply. I think for PhD students, you need to do 3 papers. Is that right? I'm not sure, but we got a paper out of one of these for PhD student. This was one of her papers where we just went and curated 20 years worth of African-American female breast cancer deaths and ran this cluster analysis on it. And those red areas, we figured out those clusters. What's the average income for those red areas? with those average areas for those blue areas, and what are the differences in age, not age, obviously, but income, race, percent minority, everything else, and we saw distinct differences between those. And they're not accidents. That's what that two-tailed t-test tells you when we work with independent samples. So take a look at some of those papers that we've done before. This week and last week were kind of, this is my major skill set. So, and I've also got a lot of verbiage in there for those papers by Lana Burwell that look at those. So now I'm just talking here, and we'll kind of go from there. So everyone online, we'll see you all later. Everyone in class, we'll see you all later as well.
Thank you, sir. Have a great week.
All right, you too.
Thank you.
All right, see ya.
Thank you.
Kimberly.
Thank you.
See you, Durante. See you, Greg. See you, Juan.